So I'll be talking about the techniques browsers or other engines are using to compile JavaScript to get the kind of impressive performance that we've been getting in the past few years. The original title of my talk suggested that I would also be giving practical information about how to write high-performance JavaScript. There will be less of that in it because actually the engines are so clever about optimizing that it's hard to break them. You have to actively try to break their optimizations. So if you're not doing anything stupid, you will get usually fast code. So Brendan introduced me. So you may know me from my book. I also wrote library Code Mirror, which was mentioned in the ACE talk before. And last year's JS1K, I wrote the winning platform game demo. Thank you. So first, I want to give some perspective about what happened with browser performance in the past, say, 15 years. So here we have the dark ages. There was Netscape 4 and there was Internet Explorer 6. Internet Explorer 6 is on the benchmarks I fed to it actually a little slower than Netscape 4 was. Of course, it supported a lot more JavaScript. These are, by the way, well, roughly, the numbers I'm giving here are completely vague and weird, and you shouldn't take them too seriously. They're based on SunSpider, but I couldn't get SunSpider to run in these two browsers at all. So I ran some of the benchmarks that did run and then interpolated to a score to be able to put these in my graph. Wait, hold on. So then there's things getting better in the middle zeros. Ajax happened and people started to actually use JavaScript for more than window open and document write. People started to write big, complicated systems in JavaScript, and thus JavaScript's performance became something serious. And browsers continued to push the envelope. Safari and Chrome were very impressive here. The green bar is Safari, orange is Firefox. Well, maybe you can read these. You can probably read them. Then we have this tiny little bar for Chrome there. And then in the last few years, you see all browsers stabilizing on tiny little bars compared to what we historically had. Part of this is that no one wants to be left behind on the SunSpider benchmark score, so they all micro-optimize for SunSpider, and this should not be taken too seriously. But yeah, things definitely got faster, got a lot faster. If you compare to 2001, that's 100-time improvement. So of course, this is like diminishing returns. You won't be expecting this kind of speed-ups in the next few years, or will be faster than C in 2 years. But there are still some things happening, and probably we'll see another speed-up of 2 or 3 times. Well, I can't promise that. I'm not writing JavaScript engines. So how do people do this? This is also pretty much the outline of my talk. There are 4 main things. Most browsers are compiling to machine code. Well, all modern browsers are compiling to machine code one way or another. There are some improvements in how values are represented. A very big thing is caching access to properties, so that you can actually look up object properties without hashing stuff and looking through big tables and things like that. Garbage collection has been improved tremendously, especially in the past few years. And of course, people are gaming benchmarks for all they can. Like there was this scandal with IE9 doing dead code elimination, but no one knows what exactly happened because it's closed source, but it seems that it only noticed that something was dead code if it was SunSpider. And maybe they've improved, maybe they've changed, I don't really know what's going on there, but also browsers are caching the result of met.cosine because SunSpider calls cosine a lot, but caching that doesn't make any sense in the general case, so they're actually probably doing a disservice to normal scripts to optimize SunSpider. There's some weird things going on. First thing, compilation. Now, the old way, the very simple way to run a JavaScript program is you parse it, you build up like a big syntax tree, and then you run over that, interpreting the tree you have. That's something you can implement in a few days. That's probably what Brendan did back in 1995. But so what you have to do is, for example, you resolve variables at runtime. So you're looking up things in scopes that you are holding in memory somehow, which have the actual variable names. And it's necessarily terribly slow, so no one does that anymore. Next step up is you compile to bytecode. This is usually a pretty high-level form of code. It's relatively easy and fast to compile to. It's small, and you get a lot of the benefits of compilation. For example, variables are resolved at compile time, and during runtime, you're just referring to, for example, a stack location and not to a name that has to be looked up. Of course, you're still running it through an interpreter. So here's an example. There's a trivial function that adds 1 to its second argument, then multiplies it by its first argument. If we take a non-existing stack-based virtual machine, the bytecode could look like this. You push 1 onto the stack, you add the 2 top numbers of the stack, combine them into 1, and replace them by that number. You multiply what's up top of the stack now, and you jump out of the function. So you notice that this is like, you reduce a lot of complexity by the compilation process, and well, it's not hard to imagine that interpretation of this will be much faster than interpretation of the raw AST tree. Next step is machine code, because then you don't have any runtime interpretation at all anymore. You're just letting the machine run your code. There's different approaches. I think V8 compiles everything it gets down to machine code right away. It's possible to compile on demand, like leave your functions in the raw form, and when they're actually called, compile them. What Firefox does is very interesting. It compiles to bytecode, it interprets that, but detects hot loops that are run to a lot, and then starts compiling those with contextual information about the types of things that are being used there. So it can compile to tighter machine code than if you're compiling for the general case. But it's a very complicated technique. Like, they try to get a whole loop to compile, and then from then on the whole loop can run without entering bytecode at all anymore. Now, the reason why JavaScript can be compiled efficiently at all, in contrast to, for example, Python, is that it is, in the end, largely statically scoped. If we have this code example, there are 3 variables. The compiler can see exactly where these variables live. X is a global, Y and Z are arguments to the function. It can decide at compile time where it's going to store them, in a register on the stack or on some global memory. The global will probably end up in global memory. And then at runtime, it just has to access that. There's some hairiness with the fact that the global object is also an object, so you can, for example, delete properties from it, and it has to check when it's accessing those variables whether they have been deleted. But because there's only one global object, it knows the object where it will be looking up those variables. And it can optimize it pretty well. Except, of course, if you do width. This became a completely dynamic scope. When looking up X and Y, it knows that they might be the function parameters, but before getting their value, it always has to go through this object scope. And so each variable reference in the program within this scope is going to take a big hit. But the nice thing is that the compiler can see statically that there is a width there. And when there is no width, it doesn't have to deal with the whole construct at all. So as long as you don't use it, you don't pay for it. Then there's, of course, the other construct that we like to talk about, eval. That also, because it can introduce new variables into the scope, it complicates scope handling. The scope has to be more dynamic. Browsers are actually much faster about handling eval than about handling width, probably because eval is used in SunSpider and width is not. So there is a motivation for this. So then here we have some beautiful moral judgment. Now, the first thing with, it's usually trivial to transform your code to an equivalent form that doesn't use with and is no more complicated. So the only place I use with is in JS1k demos. Then eval. Eval does something that's very useful, and you can do dynamic code loading. You can do, for example, compiling your templates to actual scripts and having them be blazing fast. You can do meta programming of some kind. We need eval, and the good news is that there's two kinds of eval. I mentioned before that the compiler can statically see whether a scope is completely static or not. That means only when eval looks like the red thing at the top here, when it's a direct call to the word eval, then it's a local lexical eval, which is evaluated in the scope of the function that calls it. Any other forms, like these weird things below here, are indirect. The compiler can, well, if it had to statically determine whether something is going to evaluate to the eval function, that's a halting problem, so it cannot. So what it does then, this is actually not mandated by ECMAScript 3, but I think ECMAScript 5 does mandate it. You get global eval. If you treat eval like a value, you get a function which does a global eval. And global eval is much nicer than lexical eval. It doesn't screw up your compilation. It's easier to think about because it won't override variables in your local scope. Well, you're still, of course, trusting the code that you're evaluating, but usually, this is what you want when you want eval. The line at the bottom is the nicest. You just give it a new name, and from then on, you can use that name to eval things in a more safe way. Next thing is value representation. So in a dynamic language, each value that is being passed around has to also tell its type somehow, because the code doesn't know what type it's going to get, and it has to inspect this type to know, for example, when the plus operator is applied, what it should do, whether it's concatenating strings or adding numbers. Now, the obvious way to do this is to put everything on the heap, add a type tag word at the front of the value, and then the actual value itself. So you can just inspect them. Problem with this is that you're usually making lots of numbers, for example, in your programs, mostly numbers. When you do plus, you create a new number, and when you're looping through, when you have a loop index, you're creating thousands of numbers typically. Allocating those on the heap is utterly unacceptable. So what you can do is know that every pointer you allocate, every pointer that is used by the runtime is allocated by the runtime, and it probably does want to align those pointers, like make sure that they refer to multiples of 4 or 8, depending on whether you're on a 32 or 64-bit architecture, because accessing memory words is much, much faster when these words are aligned anyway. So that means the last 2 or 3 bits of your pointers will be 0. And you can use that to distinguish between pointer values, which have the type tag in the pointed to structure, and other values. In this case, we're going to represent an integer. Engines tend to take care to represent numbers as integers as long as they can. JavaScript numbers are specified to be floats, 64-bit floating points numbers, but as long as they are integers smaller than, well, in this case, 32 bits, they can be represented as integers 32 bits as long as you detect overflow and switch to a float at the proper point. So what happens here is that you see these bits at the bottom. The top bit is set to 1 to indicate that it's an integer, and then the rest of the word is the 31 bits that are remaining is the representation of the actual number shifted to the left by 1 bit. It makes arithmetic a bit more involved, but it means you won't have to malloc to create a new number. What Firefox and possibly other engines is currently doing is representing everything with 64 bits, which has a nice property that you won't have to box your floating point numbers either, so those are also really fast and really direct. The trick is, of course, that the floating point number is 64 bits, so how do you where do you put the type tag if you're already using every single bit for your floating point number? the IEEE, I forgot the number, the standard floating point spec, which all modern architectures are using for their machine floats, defines not a number values, and actually it defines lots of those, like the last, anything that starts with 7FF or FFF and has not all zeros after that, because all zeros are used for infinity and minus infinity, is not a number value. There was some reason, I won't claim to completely understand the floating point specification, but there was a reason for this. It's sometimes apparently nice to have lots of different not a number values. JavaScript only needs one. The JavaScript standard just says that every not a number is unequal to every other not a number value. So that leaves all these other values for representing. In this case, we put the type tag. That's if you look at the yellow box, the one there would be the type tag, and then you can just put the integer if you need a 32-bit integer and the remaining 32 bits at the end. If you want bigger integers, you can even use more bits. And then if you use, say, a 2 type tag and you put the pointer in the rest of the value, you don't need to box floats anymore. And you have a really convenient uniform representation where the type tag is always present in the word itself without changing pointers. I'm told that this is a great win for Firefox, that they sped things up with this trick. Then we proceed to garbage collection. So here I have a schematic picture of a heap. You can see the gray rectangle there is supposed to represent the program, the root pointers of things that the program is actually holding on to. So I challenge you to tell me which of these blue dots are no longer reachable from blue root pointers here. That's not a trivial problem. And actually, we can see that there's like one circle that has no arrows at all there, because we can just look at the circle and there are no arrows around it. The runtime has to actually look at every single one of these blue dots and make sure that there's not a pointer in them pointing at this thing. It doesn't have like a nice high-level overview of this. It's difficult to see which memory objects are live and which memory objects are no longer reachable and can thus be collected. The usual way to do this is called mark sweep. You start at the roots and you just traverse pointers, and every time you come across an object, you mark it with a bit somewhere. If you come across an object that's already marked, you stop, otherwise you go through all its children in the same way. And then at the end, everything that's not been reached is dead, because you've proven that you can't reach it. The thing is that while you're proving this, you can't allow anyone to change anything, because it might introduce a new error which screws up your whole analysis. So typically you are stopping the world during this collection, and that's the root of the infamous garbage collection pauses in JavaScript interpreters. While it's going through its whole memory, or at least all the live memory, it doesn't let the scripts run, it doesn't let anything happen. So that's bad. There's some improvement of techniques which do this incrementally and which detect whether something changes and retrace some parts later. That helps. Another thing that helps is making your heaps smaller. Some browsers used to represent, to have one heap for all the JavaScript running and all the tabs that they had open, tabs and iframes, and it's actually a very natural thing to split that per domain, probably, because JavaScript programs are allowed to access things running on the same domain, so there can be pointers between that. But something on a different domain is almost completely isolated from other programs running on other domains, so you can just give them their own heap. That makes the problem smaller, and this makes it much faster to do a collection. Of course, if you have giant, for example, an HTML5 game, which is creating billions of objects in its own tab, then this doesn't save you, because you still have a huge heap to trace. Another very successful trick is generational garbage collection. That means you split the heap into 2 or more generations. I demonstrated with 2 here because it's quite simple. New objects go into the young generation. And then when you just collect the young generation. You promote those objects, sometimes directly, sometimes after a few collections, after they've reached a certain age. You promote them to the old generation. And at some point, the old generation gets full, so you will have to do a more expensive collection on the old generation. The problem with this is that to prove that something in the young generation is dead, is unreachable, you have to be sure that no object in the old generation is pointing to it. So you have to somehow keep track of all the pointers going from the old generation to the new generation, which requires some kind of code around every write you do, or a memory barrier on the pages that hold the old generation. This is tricky, but it's still worth it. Firefox is planning to move to generational GC. V8 had it from the start, and it's a huge win. So here's some bad pun. Consing is from the Lisp world a word that means allocating things on the heap. In the old Lisps, you could only create lists on the heap, and list cells are called consts. So in the garbage collection terminology, cons is the word for allocating. But to make something fast, to have your inner loop not cause GC passes, you should be very careful about allocating objects and arrays and anything that's going to end up on the heap. It often pays to use horrible, dirty tricks like reusing objects and setting their properties again, or setting globals instead of returning an object with several fields. One thing to be aware of is that local functions are objects which are created every time you call their, like inner functions are created every time you call their outer function. Because they're mutable objects in JavaScript, so they have to be their own object. So you have to be careful. If you're calling something a lot, don't put inner functions in it. Even if they don't close over anything in the outer function, they will still be stack allocated. There are possibilities to optimize that, but I don't think any engine does it. In my benchmarks, the functions that were using inner functions were much, much slower to call than the functions that were free of inner functions. So this is possibly the most important thing explaining the current JavaScript speed. Properties, I said before that scopes are static in JavaScript. This is great. Properties of objects are in no way static. You can dereference anything. There's prototypes to deal with. It's extremely hard to predict what an object property dereference is going to give you. So what people are doing, what everyone is doing, is inline caching. You can imagine that in the compiled code there's like a little space next to each property lookup. And when that happens, the code writes, it's going to look the property up in an object somehow, and it's going to find the offset into the object where this property lives. At that point, it stores the kind of the object and the offset of the property in this inline cache. And the next time it hits that point, it checks first whether it has a valid cache for this lookup. If it does, it can be very fast. In fact, usually there's not just, actually in all engines, there's not just one cache. They use what's called polymorphic inline caches. They have a list of hits. So that even if you have a few kinds of objects coming through there, it'll still be successfully cached most of the time. The problem is that there are no classes in JavaScript. So how do you see whether the new object you get has the same shape as the object you got the last time around? What people do is synthesize classes called hidden classes. If you know the prototype of an object and the set of properties that it has, that's actually all you need to know if they are arranged in the same order. Usually inline caches actually only depend on like the linear order in which the properties were assigned to the object because that's much easier to do. What happens is that such a hidden class has a list of successor classes. So in this case, we start with, I should have capitalized that because it's a constructor. But in this case, you get a hidden class for this function because this specifies a prototype for the new objects, and thus it will be its own class. When you have an object of this class, so when you call new point, it creates an empty object of this class, and you assign to its x, and it looks up in this hidden class in the list of successor classes whether there's one that's created by assigning x. If it is, then it takes that class. If not, it creates a new class and adds it to the list. Then the same for y. So after this, you will have uniform objects after running this constructor, which have prototype of points and x and y properties. And this class is all you need to know for caching, because if you get another object of this type, you already know where you're going to find x and where you're going to find y. This is not completely solid. It is possible to break this. I did some benchmarks, and this is the results. One noticeable thing was that both Firefox 4 and IE9 don't seem to cache lookup meshes. So if you're looking up a property that doesn't exist, it's pretty slow. Probably because some people consider this a programmer error. Depends on what you're doing. I've always happily looked for properties that don't exist in objects, but maybe I should stop doing that because you pay a small performance penalty. There's deep prototype change, which are not handled that well by Firefox. If you delete a property from an object, that's pretty hard to get back to some valid class then again, because you can delete any property, so they have to be a lot more clever than just dealing with edit properties. Both Firefox and Opera didn't deal that well with it. And then I tried just generating more and more variants, and at about 10, most caches seem to break down. If you have 10 variants of an object running through your loop, that's actually already pretty rare. You don't usually do that. What was striking when doing this, that it was almost impossible to break the V8 caching. I don't know what they're doing. Maybe I should read through the code somehow, because it's apparently very clever. Next, as a small note at the end, there's type inference. I don't think this is being done on a very large scale yet, but people are talking about it, and it's very promising, and it will probably be the next big gain for JavaScript performance. Trace compilation already takes this a bit into account, but it's completely runtime dynamic. There's actually also a lot of static information about types that you can glean from a JavaScript program. Here's a trivial example. If we take the I variable, it's being mutated in 2 points. Because it's a local variable, we can prove that these are the only 2 points that are mutating it, and they both set it to a number. It starts at 0, and then it's incremented, and the increment operation leaves it a number. So given that we know that I will always be of type number, so that means you can, for example, optimize this comparison less than. You could even optimize the array lookup. The code that the code that the compiler outputs can be a little smarter because it knows that I is of type number. There were optional type annotations being talked about in what was supposed to become ECMAScript 4. I'm actually kind of sad that those vanished, because they would help compilers a lot, even if other compilers choose to ignore them. And well, you don't have to use them if you don't want them, but I think they would be a great addition. Of course, there are other cases. If you have globals, then the whole program can change their type, and it's very hard to prove that they are going to be of a certain type. Same with properties, with the objects being passed around everywhere. Function return values. You need whole program analysis to get any kind of reliable information on these kind of values. That's exactly what Brian Hackett at Mozilla is currently doing. And it sounds like it's going in the right direction and it's very promising. I don't know how far other browser vendors are with this, but yeah, it's probably going to work to a certain point. What he talked about was that you have to dynamically update sometimes and recompile some code if your assumptions about types are broken, like anyone can do an eval which changes the type of a global, and then well, you have to go back and recompile some code, so it's very involved. But it helps, it speeds things up more. That was all. I'd be happy to take questions if anyone has one. No questions? Thank you.
You know there are planes, Chris. We didn't have to take a wagon to Oregon.